See? Who knows?
Then are you one?
Huh? Maybe.
Those were our ancestors, right?
Yeah.
But we don't call
So
them
you see
ourselves
the
like that.
tree
Yeah,
in the same
I
family.
know, but we
So
don't
it's
call ourselves
buffalo,
that anymore, right?
Buffalo, cow, same tree, same family.
Yeah, but there's a branching somewhere. Somewhere along the line they branch out, right?
Yes.
Yeah, so I don't go to the other branch, I just go to this branch.
Okay, this is the first day of the classical mechanics class, where we're going to do the Lagrangian for something that works. The basic idea of the lecture today is to get the algebra out of the way, get the Lagrangian equations derived. And we're going to do it for a system that is an ancient war machine, the Trebuchet. And we'll talk about that, and also its relation to human beings doing sports and building a culture. This is really, I think, a very important piece of history of development of the human species. So that I want to, color this with. But the part of this lecture will be a collection of equations that appear on the screen in various orders. Today I'll make the equations in sort of a matrix array that makes it clearer how this all goes together. But it will be a copy of the derivation that we've already done for deriving Lagrange's equations for polar coordinates. It's just that this device has really two polar coordinates at once. It makes its geometry is that of a torus. So all of that's going to come out. We're going to be doing Unit 2 and Unit 3 sort of on top of each other. This one is just more a standard approach to Lagrangian mechanics. This one is the approach that has all of the covariant, contravariant geometry emphasized. And we're going to start doing pieces of that even today. But mostly today it's Unit 2 of the units that I've already printed for this book and given to you in the notebooks. So the idea here really is to get into the GCCs, but right at the beginning I'll make that as simple as possible. Now this thing called the kinetic metric tensor that's the tricky thing that you, as far as I can see, you don't find in any of the other textbooks, because most of them don't pay attention to GCC. Okay, so I have here the usual references to interesting things. And then this is the gadget that we'll be playing with, as I point out in the heading here. There's Trebuchet. Last screen is the pronunciation up in the upper right hand there, Trebuchet. What does Trebuchet mean? I asked people that speak French, and they tell me that Trebuchet means stumbling about, which, I couldn't figure that out until I actually saw a very large Trebuchet over in Oklahoma, and you'll see movies of that and some of the stuff we do. When they operate, when they throw, they look like they're stumbling about. That's the best etymology I can give you at this moment for the name that came up in the all of the discussions about this. And there are quite a few references on the reference pages to the Scientific American article, and also the Smithsonian article that discusses where they try to reenact the use of a trebuchet to knock down a castle in 1215, I think, was the year that the war in Britain was occurring. It occurred right on the shores of the lake that has the Loch Ness monster. The Loch, that's Lake Loch Ness is where this occurs. This is a picture of Loch Ness, and there's a NOVA program builders from England went and tried to reenact in all of its glory and punch a hole in a wall of an ancient castle that apparently was the castle that was involved in the siege of Kenilworth. It was a big deal in England. Okay, what I would probably like to show you, and that is just a picture of this thing in operation. And before the internet went down, we were trying to build local networks here. So when you come upon this page in your lecture, this is an attempt to bypass the UA wireless and run the things. Don't use it. It doesn't do anything.
We'll back those out.
Everything here in blue should work if the UA is up. And I think they're going to stay up now. It looks like had a couple of stumbles, but they are now working.
And to qualify, if you have an internet connection and a modern browser you're in,
Yeah.
our wireless went
you
down
could
over the
use
weekend,
this,
after the weekend.
but if it doesn't work, don't worry about it. Now, I'll go ahead and just start this thing up so you can see basically what's involved here. There it is, just throwing things. But the way I've programmed this thing is after it gets done throwing the object, and let's just, one of the things I can do is slow it down just by clicking this thing down there, and then reset time equals 0. You can see what it's doing. It really picks up speed in the beginning of the throw, and this one threw something 180 feet or so. And then I just put the mass back on the thing and see what it does. You know, see the mechanics of it, and it looks pretty simple. It looks like, gee, the differential equations for this should come out pretty nicely, but they don't. This is a chaotic system. This is not a system that has an analytic solution. Even the simple version of it that we're going to be doing today, the differential equations that we're going to build, the Lagrange differential equations, we'll build today in this lecture. But the solutions are, you know, this one, you can see that it's making a pretty, it just looks like it's good old-fashioned harmonic motion. But let's see what you usually get. I can, of course, start this thing out at some different setting. You can always click on this thing, and
That'll be a good one.
and let it go upside down, sort of. And it looks like it isn't going
It didn't have
to
the
be
proper
throwing anything
angle
very
and
much.
length.
But you wait. And one thing that's missing here is it's not drawing the path. I want to have definitely drawing a path.
Well,
So
now it says no trajectories. There is something weird going on. Try solid
let's
first.
do solid. Yeah,
And then
we'll
we
just
can back
reset
that
T
out
equals
to dotted.
0.
So I could see them cross the axis, the horizontal axis, but
There we go. Okay.
Huh.
So, at first it looks, you know, well behaved, but with initial conditions I've given it, I probably have chaotic motion here. So, you can see that it's, now every once in a while you see the thing really speed up and throw something, and that's what we're looking for. That's what we're actually trying to analyze there. It's just retracing something that it did before.
display it instantly.
There's a good throw right there. It got going pretty fast,
Right
and
now.
that's kind of what we're interested in talking about today, and later on. Not so much today. I just want you to see that this thing is pretty darn complicated trajectory that it's making, and gravity is still on. The mass is still here. It just hasn't been let go, and it's making this. Let's pause, go back, and what I would probably do is compare this to this one over here, and I'm going to go ahead on this one and do the Siege of Kenilworth. I think, yes, this is the Siege of Kenilworth. This is a more This is a scale, sort of a simple thing. Look at that thing. It just throws the thing almost 500 feet. And then I put the mass back on, and you can see we've got a pretty complicated motion. And most of the time the thing isn't going very fast, but every once in a while, it just, there,
Yeah.
it just jumps, right? It just takes off, okay? And
Why-
then it stops and sort of settles back down again. And this is with no friction, gravity's on, the,
So why isn't their velocity not changing?
say again?
The velocity is not changing.
It's the
there.
terminal velocity of an object
Oh,
that's got thrown
yeah.
successfully.
After it fires once.
It's
it
not
makes a
the
number.
instantaneous.
But now it's all over the clock. And there was another one where it went pretty fast. So the reason I'll leave it on there, and eventually it'll fill its space. It's completely ergodic and chaotic motion that we've got here. And the reason I'm interested in, besides of the history and all of the, this is a terrible weapon, and I should probably mention that in other parts of the world this weapon was, after they threw all the rocks they could, they started throwing bodies. They threw plague victims. They looked for plague victims, put them on a thing, and threw it into the castle. You see, this is biological warfare. Okay. That was more effective than the rocks. Everybody got the plague in the castle. So, human beings can be really terrible. So you try to do something about that. And what I'm imagining here, making a little story of my own, I say, what if Galileo came upon this and was asked by some generals or something to figure out what's the best way to build a trebuchet, analyze this darn thing, okay, do the engineering and the physics and everything that goes with it, okay, and I say this is what Galileo might have tried to solve. What he did solve was simple pendulum. Okay, he's the first to really figure out the pendulums in the church that had nothing to do with trebuchet, okay, but why not? Why didn't he go further? Well, just think of all the mathematics and physics that had to come before you can do what we're doing right here. And even getting the differential equations which we get today, you still have to put them on the computer to get the answer. Okay, because this is not an analytic problem. So most of Lagrange's equations are fine, but particularly fine if you can put them on the computer. So that's what we're getting, setting the stage here for. But here's the other thing that I want to point out. First of all, this has now become a big deal. This is the second big trebuchet. It was built in Britain, 1998 or 9, somewhere around 2000. And that one threw a car. I mean, when they let this thing go, the car went 600, 700 feet away, upside down and crashed. Okay, so this shows you the power of this war machine. It can throw cars. That's pretty good. And then now there's a contest, in Oklahoma, where I think they're actually having one pretty shortly here. They got a lot of pumpkins, so they have a contest to throw pumpkins. And it's called the Pumpkin Chunkin. And this is a 20-pound pumpkin that's going 240 miles an hour in that particular frame right there. And that's more like the old trebuchets right here. But like anything, trebuchet gets replaced by higher tech. It's about, 1400s, actually 1500, when the Kenilworth thing is an anomaly. By this time, they were starting to make cannons. So a cannon is, a much more formidable weapon than a trebuchet. But then the metal wasn't very good, so cannons blew up. They killed the cannoneers as much as they killed the so-called enemy. And anyway, these guys just use air, and they are throwing things up to 1,200 feet. And they're trying to get more than that. as we go. Now here's where the history comes in. What the trebuchet is really doing is imitating some of the motions, throwing in particular, that humans can do. And the extreme case is throwing a bullwhip. The idea is to get this whipping motion, get some kinetic energy into some object. But think of all of the people that preceded us that had to do these things, absolutely had to do these things. This is the most common, is bringing in the grain, cutting the grain with a scythe, okay? Trying to get the kinetic energy into the blade of the scythe, right? And doing it millions of times, trillions of times, right? Just to feed the population, okay? So there's an example of, this motion, really, as the idea of that splitting a log, chopping a tree, just digging the soil, okay, with a pickaxe that takes kinetic energy, breaking rocks with a hammer, or building the railroads all over Europe and in this country. All of that stuff is, human motion that we're going to be sort of analyzing with this device. We're looking at this device as a key to human kinesiology. There's a whole area that's in this university. Kinesiology, is that the correct pronunciation? For the motion of athletics, you see. Now we don't have to do this if we don't want to, but we can't stop it. It's in our blood. You want to play baseball? You got to make a bat swing fast, right? You want to play golf? Okay, that's the most extreme case of swinging a big lever. There you get probably the most kinetic energy. You get 200 or 300 miles an hour from a golf club if you're really good. Okay, my favorite sport, tennis. Okay, the idea there is to do that without hurting yourself. And if you go to any tennis court that has people that play a lot, you'll notice there are bandages all over them. They haven't really learned the physics of swinging a lever. That's what this amounts to, okay? And there's lacrosse and a good old throwing a baseball and a football. That's part of the deal. If you go water skiing, the idea is to put the boat in such a path that you whip the skier at a high speed. Okay, that's another example of this. And then, of course, when it comes to putting our objects out in space, we do a similar thing with gravity as we send something by a planet that's in motion and whip it out to Jupiter or Saturn or finally Pluto. So this business of getting things with a kinetic energy as efficiently as possible, I think, is really important for our things. So that's the advertising part of this, the thing to realize what it is and why we're interested in doing it. We're starting to see the coordinate space fill up here in a funny kind of way with two circles of less lines than the other. And you can see that at that moment it was going pretty darn fast. So anyway, I'm going to go ahead now and cover the screens with equations. But the idea, of course, is we're talking about something that I think is really part of our culture, our lives, and if you play any of the sports, it's something you want to know about in deep details. So I'm going to stop this. You can see what's happened here. Actually, I will make sure that I pause it, but just so we don't use up CPU that we can use for something else. The basic geometry that we need to use for this is getting the coordinates and getting their differential equations, their Lagrange equations. That's what we're going to do here. And we won't stop there. Then we'll be getting the Riemann equations as well. They are, I'm going to try to do that while we're covering Unit 2, get that started anyway. write today with the Lagrange side of the story. So the basic idea is we'll have a pivot point here that's infinitely massive and friction-free. We have a huge monster of a mass hanging on a radius here. I'm using a large r to indicate the small radius and a small r to indicate the throwing, the much longer throwing radius. And then there's another radius that is another distance, a constant distance, L. And then we've got two polar angles. A polar angle phi here, which I'm going to make lab fixed. That is, this little dashed line here, this imaginary line, is going to be fixed. Later on, we're going to do coordinate transformations that have it be body-based, but this is lab-based. And this angle here is, and we're going to use the idea that right-handed is positive, looking at the trebuchet from this side, and left-handed is negative, so I'm going to start with a minus sign on both of these angles. Now I recommend you do that so that the minus, the correct sign shows up in your equations of motion, and it's a quick check to see if you're on the right track of getting the equation right, maybe first time, maybe on first try. It's not, it doesn't always work out that way, so I give you a mechanical problem like this. I'm just recommending that. You don't have to do it. In any case, the idea is when this trebuchet turns, right now it started vertical, this was left-handed motion, so that's a minus theta, and of course equal angles and equal sides there, same thing here. So we end up, when we put our sign in, that this has a minus sign. And it turns out this one does too, it's down, that one's pretty obvious. But the basic coordinates of the large mass, large X and large Y, are the just the plain old pendulum coordinates that we already talked about for simple pendulum. This has got this extra arrangement here with a pendulum that has its fulcrum moving according to the angle theta. And then relative to the laboratory, it has another angle that has to be made into a set of equations here. So, see if there's anything else I need to say about this. This is just writing down the payload or projectile coordinates are there. That's going to fly. Those will be big numbers after you've launched this thing. But right now, this is just going to be a pendulum equation, which we have written right here. So there's the Cartesian coordinates of the big mass. Now we've got to work out the Cartesian coordinates for the little mass. We have to add to the Cartesian coordinates of the radius, the big radius, another set of coordinates for the phi. So that involves the sums of sines and cosines that are up in the corner there. There's the actual projectile shown. And again, this is a theta, a phi here. But this time I put the phi in a positive position. If it was back here where we started the launch, it would also be negative. Right now I've got it as a positive, so we have a positive L sine phi right there. But this is down right here, this y is down, so that's a negative cosine the way it's starting out. Okay, so the little x and little y of this mass, and the big X and the big Y of this mass are there, ready to be made into a Lagrange equation eventually here. This is just rewriting the thing a little bit differently, just drawing the thing in a sketchy sort of way with a mass here and the big L.
So what is the
bigger
equilibrium
R.
position?
Say again?
What is the equilibrium position? The equilibrium position?
The equilibrium position for this object with gravity like that, it's pretty obvious, like that. And actually we showed pictures of that. Let's go ahead on this screen down here and show.
Good question.
Remember I said Galileo worked on this thing? At the extreme right-hand side of the three figures there, that's pretty close to the equilibrium position. The gigantic mass is vertical,
And the other mass is
Okay.
vertical.
uh,
And vertical
hanging
as
there,
well.
and the projectile holder, if it still had a mass, would be where the arrow points there. Right? Does that make sense?
Mm-hmm.
Yeah. So after a trebuchet is finished, it ends up like that, and then somebody has to yank it back down again. Now I should point out is this was a weapon that was built from about 900 AD in the West. I mean, in Europe and what we call Europe now. But the Chinese were way ahead of this. They built a trebuchet, but they did not have a big mass here. They just had about 100 guys pulling on a rope. Okay? I mean, it was just a whole army on this end of the thing, and it would be way up there, okay? And they would, oh, ready, 1, 2, 3, they would pull on this thing and probably throw the thing as far as any of the ones that were in Europe. Although we don't have much of a record on that. You have to talk to people that have really delved into Chinese warfare to learn about this. But this is 3,000 years before, okay? And if they kept building their technology that rapidly, where would they be now? It's, you know, and now they're finally just catching up and exceeding everyone. So that's a whole nother part of history that is worth learning about. In any case, as you know, once we get these geometrical equations, it's the differentials that begin our building of an equation of motion. So once we're sure that we have the correct geometry, that everything here adds up to give the little x and little y, that takes care of this mass, and then we've got this mass right here. Then we start worrying about Jacobians and differentials. Okay, but this one isn't as simple as our nice polar coordinates as single mass. We've got two things to worry about here, and that's what makes this a little bit tricky, because we do have a differential equation, differential, literally, linear equation at this point, for the large mass, okay, and we have then this more complicated equation for the thing that's going to be thrown, the projectile. So this is the driver, the red thing is the projectile, these angles right here is the thing that is most important for our motion. So it's that, and the Jacobian that we're going to be building with this, that's coming here. Here's a start. Okay, this is just a start. And you see we've got a problem because really this system is completely described by two variables. I don't need to know all about the r and little r. They're going to be constant. We're not going to change the length, at least now, of the big R right here. The thing may break and get whatever, and then this constraint relation is no good, but as long as the thing holds together and maintains its length, that sum of squares is a constant, as is, and we're going to also maintain the length of this and this, little r and little l. So both of those are constraint relations. That's the correct terminology in classical mechanics for a relation that makes the number of actual independent variables, in this case, to 2. We only have 2 really independent variables for this. This and this completely describe everything we need to do with this, and all of the other letters stand for constants. So when we write down all the partial derivatives that we have here, we have too many. It's what I call the raw Jacobian. And the problem with this Jacobian is I've got to pick out of these four rows and 2 columns, I've got to pick out 2 rows and keep the 2 columns that I have. So I've got 4 differentials to play with. That's going to make the derivation of the Lagrangian equations here more complicated than what we talked about before. So that's why I use this example. It's a good example of what happens. So what we're looking for is somewhere in this array some 4 numbers that would, maybe this would be a Jacobian. You go ahead and try it out and you discover that its value is 0. This fails completely. That's not what we want. And then maybe you try those 2 and then those 2 and so forth until you get a set that isn't singular and yet also describes the motion. This is much better. This is a successful Jacobian right here. The one that involves just the phi and the theta. And it is usually non-singular. And you can see after you've taken the determinant here, it has a very simple form. It is the product of the constant little r and the throwing arm L and the sine of the difference of these 2 angles, theta and phi. So what you notice is this thing will go to 0 when phi and theta are either equal or within pi of each other. Okay, those are 2 reasons. So this Jacobian is going to give us problems when the thing is stretched out with the angles difference by pi, or when they're equal. Okay, that's when you have the thing tucked in just at the starting point of the trebuchet, a starting point which you would never get out of if it wasn't for gravity. So otherwise, this thing is useful. It's a useful Jacobian. And it will be the one we build everything of the Lagrangian equations out of. So there's a Jacobian matrix. Here are the 2, well, one of the extremes that would give you a singular value, a determinant 0, whenever the angles are equal, or, and I didn't draw the one where it's actually throwing, that's the throwing point. We'll see that showing up here fairly quickly. So that's where we stand as far as the building of the basic Jacobian geometry. Now, we also want to see about the velocity values that we get. And x dot and y dot, both large x and y and small x and y, are the keys to getting kinetic energy. So we basically have that here just by putting a dt in the denominator, making a derivative, and that's our shorthand notation for time derivative. And while we're at it, we have to apply it as well to the driving angle theta and the projectile angle phi. They have, if you can see clearly, dots indicating angular velocities that we have. And we have to keep track of both of these because, well, this is the Jacobian that takes care of the projectile, but we also have to take care of the driver, and that's very important. But just for the projectile, we have a full, usually not 0 determinant Jacobian, and we have its transpose. So just for a nice bookkeeping, this is just a nicety. Here is a column vector, and here's a row vector, sort of a Cartesian broad-ket, if you will. I have to do the transpose Jacobian if I'm going to write a row vector made out of these velocities. So that's the row vector x dot y dot. There's the column vector x dot. This is just getting us in the frame of mind so we can deal with GCC coordinates, which we have here. These are generalized curvilinear coordinates that are anything but orthogonal. This is not an OCC problem at all. But in any case, that is the part of the projectile, and then we need as well to consider our simple relationships, x sine and y cosine, for the driver, the actual driver. So the kinetic energy, we already know that one pretty well. We know that the kinetic energy of the projectile is something like that. So we have to put both of these in the form of the coordinates that we're using here. So here is the Projectile way of writing that one. I didn't bother to do that for that one, but when I do that, I would take this bra right here and write it all the way out using the transpose Jacobian, and then I have the Jacobian here multiplying the Ket version of the angular velocities here and there. Okay, so there's your kinetic energy of the projectile. This, the kinetic energy of the driver, is a good deal simpler. That very quickly boils down to, when you take the sum of the dot squares for that, to what you're very familiar with our polar coordinates. There's your rotational inertia times the angular velocity squared, and then half of that is the kinetic energy, and then this one has this arrangement right here. So this is just a way to keep your bookkeeping straight and get ready to use curvilinear, generalized curvilinear coordinates, which this is certainly an example, non-trivial example of. Okay, so I go ahead, and this is the Cartesian expression for this, including the total kinetic energy. What we have here is the big coordinates x and y for the driver. That's the projectile. And then here is the same thing. And all it's done is I've added one little thing on the diagonal of an already pretty complicated, well, this is going to be the metric matrix is what this is going to be. So this is just showing you where all of this comes from, the Jacobian. And there is a Jacobian for this, but it only has the x and the y at one angle. It doesn't have a phi component at all. But it goes in there very nicely here with the phi dot squared. And other than that, you don't see this big driver mass in any part of the polar coordinate kinetic energy. Okay, so rewrite that in a way that makes sense with the kind of geometry that we've been talking about. And in this case, all it is, this in the Cartesian coordinates, is completely diagonal with the values of the mass, a large mass and then the smaller mass that's the projectile. It's just sitting on a diagonal. So there in the Cartesian coordinates of big X and Y and little x and y is what we call a dynamic metric tensor. It's just diagonal with the number of coordinates involved, the Cartesian coordinates involved. This is more complicated but smaller. This thing right here that we get with those angles is obtained this way, but as you recall, the products of the Jacobian, actually the transpose of the Jacobian times the Jacobian, gives you directly the metric, what we call the kinetic metric tensor of things. So we're going to see this coming back and being used just a little bit here for two things. First of all, making the Lagrange equations, but before that, making the relationship between velocity and momentum. Remember, momentum is covariant, velocity is contravariant, so we need to take that into account to make use of that whole formalism. So this is just showing the anatomy of that metric tensor. And here is sort of a rationale between that. What this thing right here is a combination of a scalar product of the partial derivatives of the coordinates of whatever mass you're talking about. So whatever device you have, there's a lot of masses and a lot of coordinates. This is kind of how you build the kinetic energy. And it would be a covariant vector dotted with another component of it summed over not summed yet, but for giving you another coefficient for each of the possible dimensions that are making up this thing. So this is an expression here of the kinetic energy, 1/2 mv squared, but being done with all of the coordinates involved. And each of those has their Jacobian times the clear coordinates. Well, that's our thetas and phis, but in general it'll look like that. So this is just bringing in a little bit of Unit 3 early into our discussion of Lagrange equations for Unit 2. So one of the things that you do when you're putting these things together is check it out for special cases. If I were to put the mass right here so that theta minus phi was 0, I would kill the Jacobian and it would be singular. The determinant would be 0. But what I get is something that's pretty obvious here. I'm going to be getting a radius r minus L here squared times whatever omega is. That would be the total rotation. Omega would be when I make those two equal. And then I would get an mr squared, that's the inertia of the driver, times omega squared. Then I would get the inertia of the projectile, which is all tucked in there with a tiny little radius, r minus L squared. So, you know, you want to check this thing out before you go and build an equation out of it, that you've got all your signs right, coefficients right. And while you're at it, you might as well check it for an angle where theta minus phi is 90 degrees. This is the angle where the maximum acceleration is occurring. So it's an interesting point kinetically. But right now I just see that what I have is a radius to this guy that's the square root of r squared plus L squared. And sure enough, that shows up correctly in the inertia of the moment for this particular guy. And this hasn't changed at all. Okay, so I'm just doing this to, you know, set you so that you have 0 defects in your building of Lagrange's equations, as well as Hamilton and all the other stuff. This is really an important step. And then it's all stretched out. This is the place in the Trebuchet, life of the Trebuchet, where we're going to let it go, because that's probably going to be where it's going fastest. Go any further than that, it's going to slow the whole thing. Everything's going to get slowed down. You can kind of see that when it's out there, that's when you want to let it go. But you want it to be at the right angle so that it hits whatever you're going to hit, right? That makes this a hard problem. And that's where Lagrange's equations will come in. That's where a computer will come in, because that's the way we solve this thing. But we should point out that the coordinates, theta and phi, if you plot them out, like I was asking you to do with some curvilinear coordinates for the problem today, there are points where that is orthogonal. That is, when it's right at the right angle point there, I can swing this guy back and forth, and it'll be orthogonal to what I get by keeping phi constant and varying the theta. Okay, so we're talking about theta and phi coordinates, and there is a particular arrangement, namely this arrangement, where they really are orthogonal coordinates, for at least in the neighborhood of that particular case. And most of the time, no, they're not orthogonal. And so it's worthwhile at this point to just look at a little bit at what the GCC look like for this crazy device. So I'm going to go ahead on both these screens here with pictures of that. There's kinetic energy being built there again. There's the metric tensor being made, and this is just showing the structure of the dynamic metric tensor in several cases. So this is where we begin the building of the Lagrangian equations. We're going to rederive the Lagrange equations while we're doing it, but this is a pretty good way to set things up so you make sure you're doing that right. So here we have the way we started our derivation of Lagrange's equations before was to look at the differential of work, that is force times distance. So back to Cartesian coordinates, we had fx dx, fy dy for the big X and Y of the driver, and then we got the same thing form written for the projectile, and then that comes down to Newton's equations, just involving x dot dot and y dot dot, and then little x dot dot, little y dot dot. So here we start off by writing the work sum as a column. It's this guy right here, that's this guy, then there's this guy, then there's this guy, and then there's this guy. We're going to be summing all this up, and that will be equal to, by Newton's law, that thing. And we're going to turn that into a Lagrange's equation before we get too far along the line here. So the first step then, just to take us through this again, is to go ahead and get basically the Jacobian relation here. This one giving us this part of the differential of work. This is the one that involves the double derivatives with respect to time. This involves just the spatial derivatives for the force times each of the coordinates. Okay, and so we're going to place this fx here with this guy right here, and so forth. Each one of these forces here, these Cartesian forces, gets replaced by a Cartesian acceleration. Okay? So far we're just working with Cartesians, but now we're letting the curvilinear coordinates, the GCC, theta and phi, come in a not too unclear motion. So here's where you assume the variables are independent. If they're independent, I could write this whole thing as d phi equal 1 and d theta equal 1, d phi equals 0. And while I'm doing that, I can go ahead and do the other. The opposite of that is to have the differential of theta be nothing and d phi be 1. So then my equations look like that. Or here it's all theta. So we're talking here about everything that the driver can do, and here's everything with only motion in the projectile. Okay, so that's a start on something here. So this is just reviewing. Remember, we did this with polar coordinates, but now we got two polar coordinates. This is Lagrange trickery. This is where the tricks that Lagrange did to make Lagrange's equations, and we're going to have two of them for two angular variables here. And so the product rule allows us to rewrite each of these expressions in that form. Okay, the derivative of this product minus x dot times the time derivative of that. That's what's going on there. And step A of Lagrange's trip. And then we have two lemmas, if you recall it. This is all in lecture 9. If you're forgetting about what we're talking about here, that's where it comes. First we have the lemma 1, which was the Jacobian of the variables, and it's true for x and y. The Jacobian for that is the same as the Jacobian of the velocities. That's all lemma 1 was. This was a little trickier because acceleration requires some extra thought. But this basically says that if you have a partial derivative of x dot with respect to q, that's the total derivative of that Jacobian component, x with respect to q. Okay? So basically we go and we replace, using this, the stuff that we're talking about. And then the final step is to realize that that's how we get a combination that involves just the kinetic energy. This is true for all of the variables that we're working with right here. So this is just the final step in the Lagrangian derivation. So there they all are, showing what will sum up to be a couple of Lagrange equations. One of them for the driver angle and one of them for the projectile angle. Driver, projectile are the two at work here. So we see here, if I just look down this column here, I've got the phi derivative of mx dot squared plus my dot squared plus mx little projectile x and the projectile little y here. I got the sum right here of the kinetic energy with respect to phi dot. And then I've got the same thing right here, the sum of the kinetic energy with respect to phi. Then I'm doing the same trick over here, sum of kinetic energy with respect to theta, sum of kinetic energy, time derivative, okay? That's in front of both of these with respect to the driver angular velocity this time. Okay? So that's it. This is just a little bit more complicated. As I say, you add up first and last columns of each variable. You get this guy right here. And you see that the thing that's different about this is this particular combination is 4 terms because that's how many variables total we have. X and y, little x and little y. Okay, so that particular generalized force, this is a definition of a covariant component, but it has 4 things, not 2 things. That's the difference between the simple Lagrangian stuff that we looked at before and what we're dealing with now. Okay? And the same thing happens with the phi variable. We only have 2 Lagrange equations, but the input, the force input, involves 4 Cartesian coordinates, and we're coming from Cartesian to these GCC, that is theta and phi. Okay? So this is the main message right here. This is rederiving Lagrange's equation for a real problem. Not that simple polar coordinate thing with one mass, right? Okay, and it involves this little wrinkle, a foursome. Okay? All right. So here it is being written out. Now remember, this is the tough Lagrange equation. This is the one that I call the 4-wheel drive garbage truck. It's the thing that takes a load of crap and goes anywhere. You can have moving coordinates, all kinds of stuff that you can throw into this thing, time dependence. It doesn't matter. With little care, you come out with an equation like this just involving the GCC force. That's the projectile one. That's the interesting one, the one that's going to go fast. And then this guy, the driver right here, same form. Okay. This one happens to not have any but 2. So this one involves 2 going to a particular component. And this one has 4 terms in it going to a particular GCC. Okay. So that's it as far as deriving this thing. Now the problem is, how do you get this on a computer and all that? But this is giving us the main structure that is involved in building that. Now, at this point, that 4-wheel drive garbage truck has to know what the force is. And we're just assuming the only outside force here is gravity. Now it affects both the giant mass, so there's a huge force right here, big M, and gravity in the minus direction, straight down. Okay, so with our coordinate systems, we can pretty easily turn that into a sum, just like the pendulum having a sine and a component of this. This is the total force that's theta is it is a function of theta, and it consists of basically two terms there, mgr sine theta and little m gr, okay, sine of theta. Let's see if that's right. Yeah, I think it is. Minus mg sine theta. Both of those forces are acting on this theta coordinate. And on the other side of the story, the gravity that's responsible here, that one requires a little bit of thinking, but there are two pieces to that one. And you want to check to make sure you've got the sign right on this, but with this sum that we're doing here, this is what we have to sum over. In both cases, there are four things that have to be summed, and that's where this comes in, and so does this one. It just involves the sign of phi. It only depends on that angle right there, regardless of where this thing is. But this one needs to have an expression here, sine theta involves the little m as well. So that's it. Those are the Lagrange equations, the Lagrange force equations. Now, as I pointed out when we did this the first time, and you might go through when you study this, check that the signs are right on this, and this is, as I say, where things can go wrong. But the basic arrows I have there for right and left indicate the sign effect. Let's see if the sign, it's spelled S-I-G-N effect on these. And I say the question here, are there plus and minus sign errors in the minus theta position is what we're talking about here. So that's where the minus comes from. And that's why I say leave the that sign alone. And keep it negative, and if it lets you have a check on this thing. Now here is where, and we're only about 25 minutes later. We've got to talk about this. This is definitely a part of this whole GCC tensor business here. This gamma mn tensor and the formulation that involves the canonical momentum. Momentum is a covariant quantity, so we want to respect that. So here is where we take this apart. Here are the equations that we've just written for this well, this partial with respect to theta dot is part of, let's see, forget where we left that last, but the basic idea is partial derivative of this thing with respect to theta dot is giving you a term here, and then also one here, so we get a cosine difference right there. That doesn't show up with anything until we have to take a partial derivative with respect to phi dot, and then that one comes out giving us this term right here. So they both have one of these things. That's a cross-metric term. That's this coefficient, and they both, one of them has a theta dot squared, and the other one is phi dot squared in there. This one involves two masses, this one involves one. Okay, see if there's anything else. That is the theorem that's going to work for all of these GC things. Whether you use the Lagrange force equation, or if we can find a potential for this, gravity is a very nice mgh potential, we'll use that, and then we'll get the Lagrange equations that we're making as our highest form of Lagrangian mechanics, and where the symmetry played a role. So, the proof of this is to simply differentiate the thing in the tensor notation. And if you do that, you come finally with this partial of q dot with respect to q dot j with respect to q dot m. That's a delta function. You get 1/2 of that, and then you get 1/2 of the expression that we want, which is the metric tensor times the velocity, coordinate velocity. And that is the, shall I say, proof that the momentum is given by our metric tensor, our dynamic metric tensor times velocity in GCC. So here's where GCC is showing a convenience, and we can do a matrix proof if you want to do that. It's a little bit cumbersome, it takes up a lot of paper. I'll go ahead and show that on this screen right here. That's just going ahead and writing the thing out as first a vector, a ket, and then the combinations that make up those, and then just taking it apart and showing that it is indeed the metric tensor times the velocity. So this is a really key equation. We're going to stick with that in anything that has to do with GCC, the coordinates. But you got to realize this is weird, because the GMN, the thing that's actually tracking distance rather than kinetic energy, doesn't have masses in it. This one has masses all over the place. One big mass here, and then little m's in every other component. Okay, so it's weird. But still, that's okay, because the momentum geometry takes that into account. That's the way to take it into account. Okay, let's see if there's anything else. This is the last part of the proof there, was just add 2 halves. Okay, QED finally. All right. And there's that thing we were just looking at. Okay, now, forces. What has this given us? This has given us something really powerful. Because you see, this device is just stressed out. There's a horrendous constraint for it here. If it isn't, this cord isn't very strong, it's going to break. And while it's breaking, the centrifugal force, the Coriolis forces, there's another constraint force right there just to hold that mass right on that lever and keep it at distance r. Okay, the centrifugal force here, enormous. Okay? So we're really assuming that this stuff is made out of good material and that these constraints hold. And what's beautiful about this is we can ignore every one of those constraint forces. They're not in the equations at all. They're 0. Now we'll prove that in a very mathematical sort of way later on, but that is the whole idea of Lagrange equations. This is again an equation where I have the generalized forces, that's P dot, theta and phi, sitting here exposed, as it were, as this is the Lagrange force equations, not like the Lagrange equations that have a potential in them. But okay, we'll take care of that if the forces that are present here that we're actually worried about, namely gravitation, has a potential formula, and it does. It's mg times altitude here, so that'll just involve the sine and cosine. But I have you compare this stuff with some of the stuff we did in chapter 12. The derivation of this was actually done in, well, this is in unit 2 of the textbook, but the stuff that we did in chapter 12 has the Lagrange equations in the form that we know and love. Okay, so if we can write the theta force has a partial with respect to theta. And it's a physicist force, so we got a minus sign here. It's the force that makes it go, not the force to hold it back. And the V also same, okay? And this is really important, that this potential is not a function of velocity. Remember we said that before, but it helps to say it again. If that's the case, then I can very easily take this f theta right here with its minus partial v with respect to theta and tack it on here and get t minus v. So there is the Lagrangian t minus v. So now we can dispense with looking at the force part of this, what we call the inhomogeneous attachment to equation of motion. It is hiding in the Lagrangian through the potential v. That's being subtracted. So that's the cool form for Lagrange's equations. The dot, the time derivative, is in this column on the coordinate. In this column, you take it off of there and put it on the p, right? So there's the complete set of non-trivial Lagrange potential equations. Elegant. But this one you have to be really careful with internal time dependence and all of that kind of stuff. This one doesn't matter if this is an explicit function of time, you just do it. But here, you gotta watch out that that thing is not an explicit function of time, or I've gotta write more stuff here. Okay? All right. Now, we do have some nasty stuff that we have to go through, but we might not get to that, because I think it's at this point that I would like to bring up something that's in Unit 3. And that was when we did our first try at a curvilinear Lagrange formalism, Lagrange equations. It was polar coordinates, and yeah, it curved, but the radii didn't curve, they were straight. Well, now I'd like to point out to you that really this doesn't work. This is having problems at the origin here, because you can, the radius, we almost always say, hey, it has to be positive. Radius has to be positive. Well, no, it can be negative. Go down this thing here, okay? So positive, negative. You got to do both. The topology kind of requires that. And we'll see several examples of that. So really the Trebuchet is double valued. It belongs to two distinct manifolds, a top and a bottom. This guy right here is in exactly the same Cartesian position as this guy. But you can see the beam is in a very different place. So this is part of that thing that happens with, and it's really annoying when it happens with wave functions, but you got to get used to it. You have to take advantage of the topology of the space that you're working with. And polar coordinates is by surface. It's just the way it is. R can be negative. We don't have to make that law that it has to always be positive. If you do, you miss out on half the problem. So that is, I think, a really key thing to keep in mind about these GCCs. So here is a picture from Unit 3 of the GCCs that we're talking about here. Here is the GCC that corresponds to, as green curves that correspond to motion that's being done by rotating the big theta, okay? So as I move theta around, I make one kind of circle. Now, you've got to realize that when I rotate theta without rotating phi, these are all lab-based polar angles. So when I rotate this thing, I got to keep this one constant with respect to the lab, so it does this. So this one traces out when it is variable, but I'm keeping this guy constant. It very obviously makes a circle. Then I move it over and I make another circle, with this mass. So there's the coordinates corresponding to Q1, which we call theta. Okay. The phi, let's see if I get this right. The phi, this guy right here, equal a constant line. That is, I'll get rid of this. This one right here is phi equal a constant, and I rotate that beam around, just all the way around, and it would cut this circle right here. So that's the, once you get used to that idea, then here is a left-handed trebuchet, and here's a right-handed trebuchet, okay? Both of them generating one side or the other of this torus. And that's the topology of this war machine, right there. Okay. And just to see that, this is another way to see it. And remember, I asked you to do a coordinate plot, a plot of a coordinate system, making one of the two. You had four variables, say u and v and x and y. One plot would be to make x and y Cartesian. That's obvious step. And then the u and v would trace out whatever curve it did. The other thing is to let u and v be Cartesian, and then x and y will be curved. Okay? That's kind of what's going on right here. Okay. I can go ahead and make the variable phi, that's Q2, and the variable theta, that's Q1. I don't see, it should have been written here somewhere, but I don't see it. Q1 equal theta, Q2 equal phi. I'm holding one of them constant, or the other one, but the basic idea is they're in a Cartesian coordinate. And the boundary between left and right is right there, where the mass is tucked in, okay? See, you don't even see the mass, it's just a little thing with a dot on it, okay? And then you come over to here, and the dot is extended. Now the mass is extended. This is the launch case right here, where you start the thing, the trebuchet, and then there's where you let it go. So along that boundary right there is the differentiation between everything inside here is a left-handed trebuchet, and everything on this side is a right-handed trebuchet, and everything on this side between here and here, that's also a right-handed trebuchet. Just, put your fingers curl in a certain direction around each one of those trebuchets. So top and bottom of this torus are those two things. Now this is more detailed, where I'm showing the covariant unitary vectors as tangents of the constant phi and constant theta lines. Okay, so as theta varies, that's where you go. You go along that. And when phi varies from that point, you go along that one. And then if you take a microscopic view of this thing, it reduces to a bunch of nearly straight lines. And I think it's a much clearer look at what that is. Okay, we've got to wind this up here, but I'm leaving you with something that I would ask you to take a look at before the next class, and that is the relationships of the Jacobian and Jacobian as far as these kinds of vectors. Remember, the way you solve problems with this is to use the columns of a Jacobian to get the covariance, and the rows of these to get the contravariance. So that is, will be the first kind of problems that we solve there. Called the tangent space and the normal space. Remember the idea of the these u vectors. This is in the normal space where I draw coordinates as though these were the things that were the bases, and then these guys get to be perpendicular. The opposite situation is over here, which we normally consider, that's tangent space. That's what we work with most of the time. Okay, I think that should be it for now. These relationships are important, and we'll talk about them at the beginning of the next class. So that's it. The tensor geometry and all that kind of stuff is important for later work. All right, have a good break. Don't break anything.